All right, new section 1.3. So in 1.3, we're talking about the average rate of change, which is kind of a, I don't know, fun section, I guess. And I think it'll make the most sense to talk about it with a bit of an application. So far, things have all been really abstract, these pretend machines that we're putting numbers into and other numbers are coming out of. But what I want to do in this problem is use a function to kind of model a real world, and there's big air quotes around that, situation. So the idea is we're going to drop a rock, and I say on some planet because if it's on Earth, then gravity works at a certain rate, and somebody will kind of nitpick that technically it wouldn't follow this equation, and blah, blah, blah. We're on some other alien planet, I guess, and we're dropping a rock from a height of 100 feet. And what we're doing is we're keeping track of its height after some amount x seconds. And this function supposedly models the height of this rock. So the way to think about it in terms of our graph is over here on the x-axis, we have time. And over here on the y-axis, we have the height of the rock. And so I guess this graph really only makes sense from like this point right here where time equals 0 down to this point right here when the rock hits the ground, right? Over here, it would be negative time, so that doesn't really make sense. And down here, the rock is like below ground somehow, and that doesn't really make sense. So I'm really just focusing on this part of the graph. So first, a little bit of review stuff. See if we can tie this together to what we've already learned in the class. One question might be, how high is the rock after 2 seconds? And while you might be able to figure this out without really thinking in the terms that we've learned so far in this class, I think it'll benefit you to think about whether that 2 would be an input or an output to the machine. Right? And well, let's see, 2 is talking about seconds, which is time, and time is on the x-axis here, so I guess that's an input. Yeah, that makes sense. The output here is the height, and the input, the x value, is the time. So if I want to figure out how high the rock is after 2 seconds, I'd find 2 here, I'd locate this point, and whatever the corresponding height is, it's a little bit hard to see in here what the height is because I've scribbled all over my graph. But whatever this height is right here, some number between 80 and 90 would be the height after 2 seconds. So the 2 would be the input, and the corresponding output would be this number, 85, give or take. I guess I could calculate it exactly over here by figuring out f of 2. That's 100 minus 4 times 2 squared. And so since 2 squared is 4, that's equal to 100 minus 4 times 4, or 16. And 100 minus 16 is 84. So I guess the output for the input of 2 would be 84. I could figure out the height of the rock. It'd be 84 feet after 2 seconds, which kind of makes sense. I start out at 100 feet, and the rock's kind of going down because gravity is a thing. And after 2 seconds, it's fallen down to 84 feet. Another type of question that I could ask is I could figure out how long it would take for the rock to hit the ground. So when the height is 0 is when the rock hits the ground. And maybe you'd want to think about it in terms of what we've learned so far in this class. The height of 0, you want to know, is that an input or an output? Well, height is the output of this machine, as we already talked about up here. So the answer to this question would be output. And we want to find the corresponding input. Really what we're asking ourselves is, what is the x-coordinate at this point right here? And it looks like the x-coordinate is what, 5? I mean, just from kind of visually inspecting the graph, it looks like x equals 5. But we could confirm that. We could make sure that when we put 5 into this machine, 0 comes out. Or maybe a better way to do it is plug in 0 as an output. So 100 minus 4x squared equals 0, and solve for the input. So let's see, add 4x squared to both sides. I get 100 equals 4x squared. Divide both sides by 4. I get 25 is equal to x squared. I take the square root of both sides of the equation. I get x equals plus or minus 5. But I want the positive solution because x represents time, and negative time doesn't really make sense in this context. So sure enough, I get this answer as 5. None of this is explicitly average rate of time, but these will be the concepts that you need to figure this out. So I thought it made sense to do a little bit of review. But if what we figured out in blue and purple kind of makes sense in the context of this problem, great, you know everything you need to be ready for average rate of change. So in the case where our machine here models position as a function of time, times the input and the position, or height in this case, is the output, then all average rate of change is the average speed. So a typical question in this section might be, find the average rate of change of this function from, I don't know, 2 seconds to 5 seconds, the 2 points that we've talked about so far. All that's asking is, what is the average speed that this rock is traveling between this point right here and this point right here? So the first comment I want to make is when you're asked average rate of change questions, you'll always be given 2 different times, time 2 and time 5 in this example. And because distance equals rate times time, like if you're traveling 50 miles an hour for 4 hours, then you just take the 50 times the 4 to figure out you've traveled 200 miles. I can take this equation and divide both sides by time and get that the rate is distance divided by time. And you're like, all right, I think I'm following so far. Well, if you are, keep in mind that the distance, the position is given on the y-axis and the time is given on the x-axis. So when I talk about the change in distance divided by the change in time, I'm really talking about the change in the y-coordinate divided by the change in the x-coordinate. And maybe you recognize that the change in y divided by the change in x is something that you're really familiar with. That's just slope. The big takeaway here, and it doesn't matter if you understand all this derivation, is when somebody asks you for the average rate. So for example, the average rate of change from 2 to 5, the average speed of this rock from time 2 to time 5, really all they are asking you is, what is the slope of this line in green? What is the slope of the line that connects those 2 points? I'll make it a little prettier because I'm kind of nitpicky like that. If I could figure out the slope of this line in black right here, I'd figure out the average rate of change. And the great news is you already know how to figure out the slope, right? We've already done that. We started that class with that. If I know that this point right here has an x-coordinate of 2 and a y-coordinate of 84, as we figured out over here, and this point down here has an x-coordinate of 5 and a y-coordinate of 0, then to figure out the slope of the line connecting those 2 points, it's called the secant line, FYI. All I gotta do is take the change in the 2 y-coordinates, so 0 minus 84, divided by the change in the 2 x-coordinates, 5 minus 2. So I get what? Negative 84 divided by 3. From this point to this point, the line travels down 84 units as it goes 3 units to the right. The slope of this secant line is negative 84 divided by 3, which is equal to negative 28, by the way. So the average speed of this rock is, it's going down, that's what the negative means, 28, and then whatever my units are. Feet per second, I guess, in this case. This might seem really confusing because we're talking about rocks and alien planets and heights and times and stuff, but really, average rate of change is a much simpler concept than maybe it seems. All you have to do is translate a question like, what is the average speed of this rock between times 2 and time 5, into what is the slope of the line that would connect those 2 points. That's it. Really, all we're figuring out in this section is slope. Before I end this video, I want to kind of tie things all together. Typically, when we talk about the average rate of change, which I'll typically abbreviate as AROC, people use a formula that might look a little bit different than the slope formula. They don't use the letter M to denote it, even though really it is just the slope, but it's the slope of the line connecting these 2 points. And maybe for slope, you're familiar with y2 minus y1 divided by x2 minus x1. For average rate of change, typically the way it's written is f of x2 minus f of x1 divided by x2 minus x1. But really, this formula is the same as this formula because the y coordinates are just the f of x coordinates. The output of the function is the y coordinate. But the reason it's written this way is because average rate of change questions are typically asking about functions. So instead of saying y, it's written in function notation. But if you can make the connection between this formula, which maybe is the new one, and this sort of old formula for slope, then really there's nothing new to memorize or learn in this section. One last comment that I want to make is this question that I answered up here, I kind of did it with a combination of sort of a geometrical interpretation by looking at the graph and an algebraic interpretation by looking at this equation. But really, we could have done it either way. We could figure out the slope of the secant line just by looking at the graph, so by coming up here and recognizing that this point is at 284 and this point is at 50. Or without ever having the graph at all and just looking at this equation, putting 2 and 5 into this equation and figuring out that 84 and 0 would come out respectively. This video is supposed to just introduce average rate of change, although I think I kind of ended up showing you everything that you need. In the next videos, really all I'll do is get a little bit of practice and then show you how once you understand sort of this base, we can do some kind of cool stuff with this. But that's all in future videos. I'm going to stop this one here.